Welcome to Electrical Lad, your trusted source for simplifying electrical, hydraulic, and pneumatic concepts in a clear and practical way. If you're new to this channel, don't forget to subscribe and tap the bell icon to stay updated on our latest videos. Electricity and fluid power can be dangerous. Always ensure you are properly trained and qualified before working with these systems. In today's video, we're going to design the hydraulic and control circuits for a simple 100-ton press with a 24-inch stroke. We'll walk through how to select the right hydraulic components, like the cylinder, pump, and valves, and then build a basic control system to operate the press safely and effectively. Most industrial presses, whether they're 2-ton or 400-ton, follow the same core principles. This example will give you a clear and practical approach, without unnecessary complexity. So let's dive in. The first step is to pick a cylinder bore size and calculate the pressure needed to generate a 100-ton force. We don't yet know if this size is ideal. We're just starting with an assumed piston diameter of 12 inches or 30.5 centimeters to see if the required pressure falls within a practical range for our design. Now, force equals pressure times area. That's the basic formula. So, to find pressure, we just divide the force by the area. In our case, the force is 200,000 pounds, and the area comes from a 6-inch radius circle. Do the math, and that gives us a pressure of about 1,769 psi, or roughly 122 bar. Now, here's a good rule of thumb. The available pressure should be about 130% of the calculate pressure. So, in our case, the pump should be able to handle around 2,300 psi, or 124 bar. But that brings up the next big question. At what volume? To find the volume, we just multiply the area by the stroke. In our case, the stroke is 24 inches, and the area is 133 square inches. Multiply those together, and you get a volume of 2,712 cubic inches, which is 11.7 gallons, or 44 liter. To choose the right pump, we first need to know the flow. And to figure that out, we have to know how long it takes to complete the 24-inch stroke. In our design, it takes 1 minute. So, the calculated flow is 11.7 gallons per minute, or about 44 liters per minute. However, a good rule of thumb is that the pump should be 120 to 130% of the calculated GPM. So in our case, that means the pump should be able to deliver 15 gallons per minute, or 57 liters per minute, at 2,300 psi, or 124 bar. When selecting our pump, we typically have 3 options: a pressure-compensated pump, a variable displacement pump, or a gear pump. The gear pump is the most economical choice. A typical mid-size gear pump can handle around 20 gallons per minute at 3,000 psi, making it a solid option for many standard applications. On the other hand, pressure-compensated and variable displacement pumps are significantly more expensive. However, they're better suited for higher pressure and flow rates and more advanced hydraulic presses. Now that we've selected our pump, the next step is choosing the right directional control valve. Since we're using a positive displacement gear pump, we need to go with a tandem center valve, not a block center. The tandem center allows oil to return to the tank when the valve is in the neutral position. This prevents pressure buildup, reduces heat, and minimizes wear and tear on both the pump and the motor. By the way, if you're not familiar with hydraulic symbols or how different valves work, I recommend checking out my video titled 30 Years of Hydraulics in 17 Minutes. It's a fast-track overview that'll help everything make a lot more sense. Now, the pump pressure is set by the relief valve at 2,300 psi. That's about 30% higher than the 1,800 psi required to operate our 100-ton press. To control this, we'll use a pressure switch and set it at 1,800 psi. When the system reaches that pressure, the switch will trigger the circuit to stop building pressure and begin retracting the cylinder. I'll show you exactly how that works when we go through the control logic. If you're finding this video helpful, make sure to hit the like button, subscribe to the channel, and turn on the notification bell. Next, let's talk about the pilot-operated check valve. You can think of it like a safety brake for the cylinder. When the cylinder is holding position, whether fully retracted or anywhere along its stroke. The check valve locks it in place and prevents drifting. This drift could be caused by the overhung weight of the load or by internal leaks, especially through the directional valve. The check valve stays closed unless the pilot line senses pressure. That pilot pressure only appears when the directional valve shifts to extend the cylinder. In other words, the valve only opens when it's safe to move, helping us maintain control, eliminate drift from leaks, and prevent any unwanted cylinder movement. Next up is the counterbalance valve, and you might be wondering, why do we need it? A counterbalance valve is critical when you're working with a large cylinder rod or a heavy platen, like we are here. Here's the issue. With no counterbalance valve in the circuit, when the directional valve shifts to extend the cylinder, the rod end port connects directly to the tank, dropping the pressure on that side to zero. Without resistance, the weight of the platen could cause it to drop uncontrollably, basically a free fall. The counterbalance valve prevents this by holding back just enough pressure at the rod end. This keeps the load stable and only allows the cylinder to extend in a controlled manner. So how do we calculate what the counterbalance should be set to? We'll go over that next. The first step is to calculate the annular area. That's the area on the rod side of the cylinder. Because the rod is attached to the piston on that side, it takes up space and reduces the surface area where hydraulic pressure can act. As a result, the rod side produces less force than the cap end. To calculate the annular area, we take the piston area and subtract the rod area. In this case, the rod diameter is 10 inches, which gives us an annular area of 34.5 square inches, or approximately 223 square centimeters. This value is essential for setting the correct counterbalance pressure, which we'll cover in the next step. Again, pressure is calculated using the basic formula. Pressure equals force divided by area. Since our rod is 10 inches in diameter and 24 inches long, it adds some weight to the system, 533 pounds, to be exact. When we add that to the 2,000-pound platen, the total force becomes 2,533 pounds. Now, we divide that force by the annular area, which we previously calculated as 34.5 square inches. That gives us a pressure of 73 psi, or approximately 5 bar. This is the minimum back pressure our counterbalance valve needs to hold the load and prevent the platen from dropping. Now, as a rule of thumb, the counterbalance valve should be set to 130 to 150% of the calculated pressure. In our case, we calculated 73 psi, so multiplying that by the rule of thumb range gives us a safe setting. For this design, we'll set the counterbalance valve to 100 psi, or about 7 bar. This ensures controlled movement while safely supporting the load. Next, we need to calculate the horsepower required to run the hydraulic pump for this press. Now, keep in mind, even though the relief valve is set at 2,300 psi, our pump is rated for 20 gallons per minute at 3,000 psi. So to be on the safe side, we'll calculate the required horsepower based on the maximum pressure and flow the pump can deliver. To calculate hydraulic horsepower, we use this formula. Horsepower equals pressure times flow, divided by 1714, then divided by efficiency. In this case, we're working with 3,000 psi and a flow rate of 20 gallons per minute. So 3,000 multiplied by 20, divided by 1714, and then divided by 0.85, assuming an efficiency of 85%. That gives us a required horsepower of about 41 HP. Since motors don't come in that exact size, the closest standard option is a 50 horsepower motor, or roughly 37 kilowatts. Next, let's talk about hydraulic tank size. A general rule of thumb is that the reservoir should hold 2 to 4 times the pump's flow rate in gallons per minute. The exact size depends on the system's cooling and filtration setup. Since our system includes a cooling unit, we can go with the lower end of that range, a 2x multiplier. With a 20 GPM pump, that means our tank should hold around 40 gallons, or roughly 150 liters. This ensures the fluid has enough time to cool, deaerate, and settle contaminants before being recirculated. Now that we've calculated the horsepower requirement and determined the tank size, it's time to think about cooling. As we discussed earlier, our system requires about 41 horsepower, and with a 20 GPM pump, we chose a 40-gallon tank, assuming a 2-to-1 ratio, because we have a cooling system in place. But here's the thing. The size of that cooling system depends heavily on the duty cycle of the press. If the press only runs a few times per shift and the tank is large enough, then the oil has time to cool naturally, and you may not need a cooler at all. But in our case, the press operates continuously, so the heat generated doesn't have time to dissipate on its own. That's why we need a heat exchanger. But how do we figure out the right size? Let's break that down in the next step. An easy and crude way to estimate the cooling requirement is to use a rule of thumb. We assume that about 30% of the total hydraulic horsepower is converted into heat. In our case, we calculated the system requires 41 horsepower. So, 30% of that is about 12.3 HP, which translates to roughly 9.2 kilowatts of heat. To convert that into BTUs, we multiply by 3,412, giving us a cooling requirement of around 31,475 BTU per hour. For this setup, we'll go with a shell-end tube heat exchanger, controlled by a temperature switch that activates cooling only when needed. This keeps the oil temperature in check and protects the system during continuous operation. The last part of our hydraulic system design is filtration, and it's a critical step to ensure long-term reliability. First, we have the suction filter. This is typically a 120-micron filter placed inside the tank on the suction line of the pump. Its main job is to catch large particles and debris before they enter the pump. Next is the pressure filter. This one plays two important roles. First, if the pump fails or components break apart, the pressure filter will catch the debris before it can damage valves and other critical parts. Second, depending on the micron rating, it can block even the smallest particles, especially important when using servo or proportional valves, which are sensitive to contamination. And finally, we have the return filter. This is usually rated at 5 microns, and it cleans the oil as it returns to the tank, keeping the reservoir as clean as possible for the next cycle. Proper filtration at these 3 points, suction, pressure, and return, is the key to maximizing the life of your hydraulic system. Now that we've selected all the hydraulic components and completed the necessary calculations, it's time to design the control system for this press. But before we dive deeper, if you haven't already, hit subscribe, tap the bell, and drop a like. It really helps the channel. Now let's get back to it. For the control system of this press, I'm using the ACE 11 Compact PLC from Velocio.net. It's a great little controller with 6 discrete inputs and 6 discrete outputs. That gives us plenty of outputs to run the press, but not quite enough inputs for everything we need. So, to bridge the gap, I'll be using some old-school relay logic, specifically to control the motor and the cooling system. This actually works out well, because you'll get to see how PLC programming and relay logic can work together in the same system, giving you a solid understanding of both. Since we don't have the actual input devices, like proximity switches or palm switches, I'll be using a dip switch simulator to mimic those signals. It's a simple way to test and debug the PLC program, without needing the full hardware connected. For the outputs, I'm using a status light that changes color depending on which output is energized. This gives us a quick visual indication of what's happening in the system. Now let's take a look at the electrical diagram for this press. First, we have the power source, which is a 24-volt DC power supply. Next, to protect the circuit, we're using a 3-amp fuse. This helps prevent damage in case of a short circuit or overload. Next, we have the master control relay, which is responsible for powering up the control circuit. This is a latching circuit, meaning once the momentary normally open on push button is pressed, the master control relay gets energized. When that happens, contacts MC1 and MC2 close. MC1 acts as a jumper around the normally open on switch, keeping the circuit energized even after the push button is released. Meanwhile, MC2 supplies power to the rest of the circuit, including the PLC, input and output devices. Next is the pump motor, which uses a latching circuit, but instead of a basic relay, we're using a motor starter with built-in overload protection. This is represented by the normally closed contact on the right side of the diagram. So, if there's an overload on any phase, the motor will trip and shut down automatically, protecting the system. As I mentioned earlier, I may not have enough inputs available on the ACE11. So instead of using the temperature switch as a PLC input and writing a program for it, I'll hardwire it directly into the circuit. When the oil temperature reaches 130 degrees Fahrenheit, the switch closes, which energizes the cooling valve, allowing water to flow through the heat exchanger and cool the hydraulic oil. Now let's take a look at the press inputs. First is the up proximity switch. This is a normally closed switch, meaning when the press is fully up, the switch opens or drops out. Second is the down proximity switch, which is also normally closed. When the press reaches the bottom position, this switch opens. Next is the start cycle selector switch. This is a maintained, normally open switch that must be closed for the press to operate. Without this switch in the on position, the press won't move, no matter what other inputs are active. Then there are the two-handed palm switches, also known as a two-hand anti-tie-down circuit. These are momentary, normally open switches that the operator must press at the same time with both hands to initiate the downward motion. If either hand is released, the press cycle will stop. This is a crucial safety feature that helps ensure the operator's hands are clear before the press moves. Next is the pressure switch, which is normally closed. When the system reaches the squeeze pressure, in our case, 1,800 psi, the switch opens, signaling the control system to retract the cylinder and move the press up. Finally, we have one more input that's not on the press, but it is in the control panel. It's a normally open auxiliary contact from the pump motor starter. This contact closes only when the motor is running and acts as a safety interlock. If the pump isn't running, the press won't activate. Keep in mind, this is a basic press setup. More advanced presses may include additional safety devices such as light curtains, safety relays, and category-rated controls to meet higher safety standards. Now let's take a look at the actual wiring diagram of the ACE11 input side. On the left, you'll see how the actual field input devices would be connected to the input terminals. In this setup, we're using the 24-volt input power as indicated by wire 71 from the master control circuit. On the right, I've shown the inputs using a dip switch simulator, which we'll use to simulate each input manually during testing. Important note, the dip switch simulator uses the internal 5-volt power supply provided by the ACE11, not the 24-volt power from wire 71. Now let's look at the output side of the ACE11 PLC, which is very straightforward. On the left, I'm showing the actual outputs connected to the press. Output 1 goes to a buzzer that sounds an alarm when the pump is not running. Output 2 is wired to solenoid A on our directional valve, which controls the retract motion. Output 3 goes to solenoid B, which handles the extend function. On the right, we have a stack light with a buzzer that we'll use to simulate these outputs during testing. Output 1 connects to the buzzer on the stack light. Output 2 is connected to the blue light, which signals retract. And output 3 powers the green light, indicating extend. Now that we've assigned the inputs and outputs, it's time to start programming the ACE11 PLC for this press. The first rung in our logic controls the press's downward movement, or in other words, the extend cylinder cycle. To begin this movement, several conditions must be met. The auxiliary contact from the pump motor starter must be closed, confirming that the pump is running. The cycle start selector switch must be in the on position. Both palm buttons must be pressed at the same time. This satisfies the two-hand anti-tie-down requirement. The pressure switch is also normally closed in the field, but we show it as normally open in the logic because it will open when full pressure is reached around 1,800 psi, signaling the end of the downward stroke. The press-down proximity switch is also normally closed, and since the press hasn't reached the bottom yet, this contact is still closed. The press-up proximity switch is a normally closed switch, but when the press is at the top, it opens. So in our logic, we show it as not made, because it's actually open at that moment. Once all these conditions are true, output B is energized to extend the cylinder. But here's the important part. As the press starts moving down, the press-up proximity switch will change state. If we don't latch the output, it will de-energize. So, we use a latch with an auxiliary contact from the output itself. This keeps the press moving until it fully reaches the down position. Now let's look at the retract logic for this press, or in other words, the cylinder return cycle. Just like the extend cycle, we still need to confirm that the pump is running using the auxiliary contact from the motor starter. The cycle start selector switch must also be on, and both palm switches need to be pressed. We also need to include the press-up proximity switch contact in the circuit. Since it is a normally closed switch, it remains made while the press is down. It only opens once the press reaches the top position. We'll use this contact to break the circuit and turn off the retract output once the press has fully retracted. But for the retract cycle to begin, we introduce either of two additional conditions. First, the pressure switch must be open, which indicates the system has reached the full squeeze pressure, around 1,800 psi. Second, the press-down proximity switch must also be open, confirming the press has reached the bottom of its stroke. Now, because the press is usually squeezing something during operation, the pressure switch often opens before the press-down proximity switch does. That's why we allow either of these two conditions to trigger retraction. If the press-down proximity switch opens instead, it likely means we're dry cycling or the pressure switch didn't activate, but either way, the system will proceed to retract by energizing solenoid A. Finally, we need to latch around these two input conditions using the output coil for the retract cycle. That's important because once the press starts moving up, both the pressure switch and the proximity switch will drop out, and without the latch, retraction would stop mid-cycle. Now, let's take a look at the third rung of logic. This rung is designed to alert the operator if the pump motor isn't running. When the cycle start selector is turned on, but the auxiliary contact from the pump motor is not made, the alarm buzzer is triggered. This provides a clear indication that the pump motor has failed to start. Now, let's simulate our logic. On the dip switch simulator, to start the cycle, we need several switches turned on. The auxiliary contact from the pump motor must be made, showing the pump is running. The press-down proximity switch must also be made. It's normally closed, meaning the press is not down. The cycle start selector switch must be on, indicating the system is ready. And the pressure switch must be made as well, since it's normally closed until the press reaches 1,800 psi. Now let's run the simulation. As you can see, the four switches we discussed earlier are turned on, and the press-up proximity switch is on, meaning the press is at the top. When we activate the two-handed palm switches, the press extend output energizes, and the press begins moving downward. Now, note that the extend output is latched around the press-up proximity switch. This ensures that when the press starts moving down and the flag moves away from the proximity sensor, the press will continue moving downward without stopping. Now, once the pressure switch opens, meaning the set pressure has been reached, and the two-handed palm switches are still made, the press automatically starts the retract cycle. Another way the press can start retracting is if the press bottoms out and the flag triggers the press-down proximity switch, confirming the press has reached the bottom of the stroke. Finally, if the cycle start contact is made but the pump is not running, the alarm will sound to alert the operator. Also, at any time, if the operator removes their hands from the two-hand palm switches, the cycle will immediately stop. And that wraps up the design, wiring, and programming of our simple hydraulic press control system. I hope this gave you a clear understanding of how to design a basic hydraulic press and its control system, along with how relay logic and PLC programming can work together on a simple project. If you found this video helpful, please give it a like, subscribe to the channel, and hit the bell so you don't miss future videos. Thanks for watching, and I'll see you in the next one.